Hello, I am Won-gi Hong, a professor of Department of Architectural Engineering at Kyung-hee University, Seoul, Korea. I'll be talking today auto-design based optimization of pre-stressed frames using artificial neural network based Hong and Lagrange algorithm. This work was supported by the National Research Foundation of Korea grant. The Lagrange method was developed to find optimized solutions for objective functions based on constraints including equality and inequality conditions. In the present study, the Lagrange method is implemented in optimizing the design of structural frames. The structural frames shown in here are pre-stressed and non-pre-stressed concrete frames, and this study optimizes the pre-stressed and non-pre-stressed concrete frames using the algorithm referred to ANN-based Hong and Lagrange algorithm. The difficulty of implementing the Lagrange optimizations arises when the explicitly mathematical derivation of the objective and constraining functions are complex, such as the structural frame that are optimized in this study. The ANN-based functions can replace the explicit functions for an easy application of the Lagrange optimizations. As the first step, big data sets are prepared. The 111 output parameters you see in the screen right now are 200 times repeatedly calculated for given 38 input parameters, as you see on the screen, subjected to 198 load combinations. As required by code such as ASCE 318-19 and ASCE 7-16. Structural mechanics-based software ABBA stands for AI-based design of building applications. Let me just go through one more time how to generate 200,000 big data sets. For the big data sets, 111 output parameters are 200 times repeatedly calculated based on 38 input parameters based on 198 load combinations. And design parameters, constraints, and objective functions for optimizing pre-stressed frames using ANN-based Hong and Lagrange optimization as shown below. We have here 38 input parameters and 111 output parameters. These two types of parameters will be used to calculate the data sets, big data sets, whereas we have 213 design constraints, and these design constraints are used to solve for the settle point of Lagrange functions. And from the output parameters, there are four important parameters called objective functions. Four objective functions are cost function, structural weight function, CO2 emissions function, and energy consumption functions. See here 111 output parameters in the big data sets, which are calculated based on 38 pre-assigned input parameters. In the second step, this is how the neural networks for cost and CO2 emissions look like, which is mapping 38 input parameters into 111 output parameters with 4 prescribed hidden layers and 64 neurons. From the neural network we see in the middle of this page, we can count horizontally to get a number of layers, whereas counting vertically, we get a number of neurons. This is a feed-forward artificial neural network, whereas networks are nested in terms of weight and bias matrices from the first hidden layer to the upper layer for predetermined 4 layers and 64 neurons. Weight and bias matrices are obtained by training networks on 200,000 big data sets. Weight and bias matrices are revised at each epoch through the backpropagations. Dimensions shown in the bracket indicate matrices sizes. For example, 64 by 38 represents 64 neurons and 38 input parameters used in the network. Quite a big size of matrices. And here we have a weight matrices and bias matrices which are nested throughout the feed-forward artificial neural networks, which are identified by training networks on 200,000 big data sets using the backpropagations. As the last step, Lagrange function considering multi-objective functions is established to minimize meeting 213 constraining conditions for the frame design of this study, by which 38 design parameters converge to the saddle point of the Lagrange function for the optimized solutions. These are the constraining equations selected for the pre-stressed frames, including requirements for equality and inequality conditions. We have camber requirements, lever ratio requirements, diffraction requirements based on the design code we are looking at. Here we see 38 design parameters that converge to the saddle point of the Lagrange function considering multi-objective functions subject to 213 constraining conditions. The 38 design parameters were used to forwardly calculate output parameters including objective functions. Red dots represent the designs on the Pareto frontier obtained for different Pareto fractions. They provide the designs performed reflecting contributions of each objective function to the overall optimizations. For example, design point number 1 up there yields the design parameters in which the cost target is 100% optimized, whereas the optimization of the weight objective function is ignored. And the other way around, point 9 yields the design parameters in which the optimization of the cost target is ignored, whereas the weight objective function is 100% optimized. In between the two extreme optimizations, the Pareto frontier will lead the engineers to uniquely optimized design parameters depending on the Pareto fractions, as can be seen in the frame sections. The engineer can select Pareto fractions or contributions for each objective function to the broad optimization according to the design targets or design nature. The 10,416 green designs are the designs that were filtered through the constraints from the entire 340,000 black big data sets randomly generated. By the brute force method, it is verified that the lowest boundary of the 10,416 data sets filtered from 340,000 data sets are well predicted by the Pareto frontier, as can be seen in the figure you're looking at right now. Okay. Reductions of the cost and weights of the frames based on Pareto designs are represented by the differences between the Pareto design and vertical and horizontal blue lines respectively. See, the frames with 11 staggered story 5-rack frame with one bay are optimized using parallel designs, in which the reduction of the cost is seen by the differences between the parallel designs and vertical blue lines, whereas the reductions of the weight is seen by the differences between the parallel design and horizontal blue lines, as you see over here. Okay. The reductions of the cost, CO2 emissions, energy consumptions, and weights of the frame are observed up to 32, 38, 37, 5% respectively by comparing ANN-based optimizations with the minima of the datasets identified based on 10,416 green design filtered from 340,000 datasets. These are the design examples for the pre-stressed and non-pre-stressed frames. The optimized frame sections based on 9 parallel fractions are presented in the following comparisons, whereas the multi-objective functions are optimized simultaneously. What you see here is the comparison of sections for columns. The first column section, the bottom of the slide, you see the column sections and levers when optimizing weights 100%, whereas the optimization of cost is ignored. The second section represents the section where we have optimized cost 100%, whereas we ignored the weight 100%. Okay, as you see over there, when you optimize cost 100% while ignoring the weight of the sections, you want to use concrete section, which is cheaper than the metallic materials such as rebars, so that we need to use a concrete as much as possible, whereas we have to use the rebars as small as possible, so that we end up with a big sections which is 440 by 561 over there, whereas we have a rebars 12 T13 diameters, 4 T16 diameters, and 419 diameters. And if you take a look at and compare the sizes rebars sections that we obtained when we optimize the weight. When you optimize the weight, we want to use a smaller concrete sections and want to use more rebars to reduce the weights. And we end up with a small sections which is 400 by 550, and rebars are quite big. Instead, for the diameter 13 rebars and 12 diameter 16 rebars and 8 diameter 19 rebars, so that very two distinct sections were compared very clearly for the case where we want to optimize cost or we want to optimize weight, so that we end up with the big sections, the big concrete, but with small metallic material which is expensive. And this is how the parallel frontier come up with when we want to optimize two objective functions simultaneously. We have the result for the non-pre-stressed frames similar to those that we obtained for pre-stressed frames. Here we have parallel frontier, the one shown on the top of the slides, where we have a cost. The very first design point is obtained when we optimize cost, whereas we ignore the optimization of the weight. WCI is equal to 1, whereas WW is equal to 0. Whereas we have the last point represents WCI equal to 0, representing the optimizations of cost is ignored, whereas WW equal to 1, where we have weight optimization for 100%. And the two extreme cases are showing, whereas the rest of the designs based on parallel frontier and parallel fractions obtained while optimizing the multiple objective functions simultaneously. They are indicated in between the two extreme design cases. For example, we have here the third point represents we consider 75% of optimization for cost, whereas we have considered 25% of optimizations of the weights. Well, we can take another point. Second last is probably WCI is 0.125. We consider 12.5% for optimization of the cost, whereas WW is equal to 0.875, which means that we consider 87.5% of optimizations for cost. So we all can obtain and identify designs depending on your preferences or based on your design natures using the parallel frontiers and based on parallel fractions. And the sections are shown there. If you take a look at the first section based on design point number 1, where we have optimized the cost only, we ignore the optimization of the weight. Where we have a relatively big section compared with the section that we apply design point 9, where we are ignoring the cost, whereas only the weight is optimized 100%. The section is 590 by 590. The bar is 7,681 millimeter square for design point 1, where we have optimized cost only, whereas we have a smaller section which is 499.8 by 499.8. The libars are 19,604 millimeter square. So we have smaller sections and we have large libars whenever we want to optimize or minimize the weight of the section while we ignoring the cost. This is very interesting analysis based on ANS that we can consider any design concepts, any design preferences, any design references. The sections are accordingly identified based on the Pareto fractions. Okay. Now we have very interesting tool based on AI that calculates and optimized frame sections holistically based on Pareto fractions. The Pareto fractions are determined based on design targets or design natures or design preferences. That gives us the section sizes accordingly. Okay, we need the bigger computer power to design and optimize higher building structures, but the algorithm is provided so that we're ready to go for and design high-rise buildings upon using big computers. And this is the way that we can reduce the CO2 emissions and cost and energy inputs. And this study, auto-design based optimizations of pre-stress and non-pre-stress frames using an artificial neural network based on Hong and Lagrange algorithm is developed. This study developed AI-based structural design of multi-story frames achieving auto-design and auto-optimization, which will lead to a reduction of CO2 emissions, energy consumptions, and the cost as well, contributing to providing sustainable and robust designs for the era of the climate crisis. Hope this study is dedicated to the solution of the climate crisis. Thank you.